Bismillah ar-Rahman ar-Rahim. This is a statics class delivered by Dr. Qusay Al-Kaseasbeh from Mutah University. Today, inshallah, we're going to start with Chapter 7, Internal Forces. The chapter objectives are: we need to use the method of sections to determine the internal loadings in a member at a specific point. يعني راح نستخدم method of sections اللي شفناها and let's say in a truss. So we're gonna make an imaginary section at some point to find the internal loadings in this member. And we need to show how to obtain the internal shear and moment throughout a member or over a member and express the results graphically in the form of shear and moment diagrams. يعني we will teach you how to draw shear and bending moment diagrams. كيف نرسم الشير والbending moment diagrams. If we do have time, we can analyze the forces and the shape of cables supporting various types of loading. راح نحكي عن الcables. Okay. So to design a structural or mechanical member, we need to know the loading or the internal loadings acting within the member to make sure that the material can resist the loading. يعني حتى نصمم structural member, let's say, لازم نعرف loading which is within the member, so we make sure that the material of this structural member can resist the applied load. يعني ممكن تقاوم اللود المطبق عليها. In this case, the internal loadings can be determined by making an imaginary section and find these forces. Let's take an example here and see how we're gonna do that. So if we do have such beam here, this is a cantilever beam, okay, loaded with P1 at this point and inclined P2 at this point. If we take a section at point B here, so this section will be like this. So here, this is a fixed, so we do have three support reactions. This is AX, a horizontal force component, AY, a vertical force component, and we do have a moment. So this one we know how to get it, okay? Right now, if we take a section here, we need, or we will have a normal force. This is a normal force. They call it MB here. This force all the time is perpendicular to the cross section of the section. Okay? راح تكون دائما perpendicular على the cross section, يعني عمودية. We do have a tangent force اللي هي هون VB. We call it shear. هاي بنسميها shear. Okay. We do have a bending moment here. It's MB. Okay. Similarly, if we take the right segment here, we do have MB perpendicular to the surface. طبعا MP هون و MB هون, they are equal to each other, opposite in direction or direction. Similarly, we do have shear force here, VB, which is equal to this one, and they are opposite in their direction. And we do have a moment here, and the moment same magnitude and opposite in direction. This is counterclockwise, this is clockwise. Means, if we get these two segments or pieces back together, إذا رجعناهم مع بعضهم, all these forces will be cancelled out. يعني each of these forces, this will cancel this. Shear will cancel with the other shear force here. The moment they will cancel this. So we'll get back and we have no forces if there's no cross section here or imaginary section. Okay. To solve a problem in two-dimensional plane, we need to, let's say, assign the sign convention. And we need to assume the sign convention. Yani, where is the positive, where is the negative? So as I mentioned, if we have an imaginary cross section, we do have normal force and shear V and bending moment M. طبعا sign convention can be arbitrarily assigned. Yani it's a arbitrary process يعني ممكن تختاره بطريقة عشوائية or randomly, okay? But there is widely accepted sign convention. This one here, guys. So if we have or this piece of, let's say this is a structural member piece. Normal force will be positive if it's tension. يعني هي باتجاه away from the cross section فبنعتبر normal force هون positive ماشي. If we do a cut here إذا عملنا cut هون يا شباب ف let's say this piece which is, let's call this 1, let's call this 2, okay? So this piece have a normal force here which is this force here, normal force, and to keep this in equilibrium, we should have another force here. This is a normal force at the imaginary section, okay? Same here, this is, if this is 1 and this is 2, which is this one. So we do have a normal force here, which is this one. And to keep it in equilibrium, we need to have another force here. So this is going to be in equilibrium, this is going to be in equilibrium. The point here, it's going to be positive if it's a tensile force. For the shear, it's going to be positive here. Let's talk about this one. It's going to be positive if the shear rotates the piece of the structural member clockwise. يعني إذا الشير بيعمل أو بيخلي هاي segments تلف مع عقارب الساعة فبنعتبره positive. I'll show that later more than this, okay? يعني هون يا شباب if we do have this, okay, V هون, so this one is going to be positive لأنه هذا فعليا it's going to rotate to the clockwise. Similarly here, this one is going to be positive to this way. For bending moment diagram, if we have this piece here, so the moment will be positive if it's going to bend the structural member piece upward. يعني إذا عمل فيها هيك. Just a minute here شباب. Okay, let me clear all. So if it's this one bended like this, so we do have positive bending moment. To clarify the sign convention again, if we do have a cross section like this, it's a beam, okay, it's a beam. And we do wanna make an imaginary cross section here. Call it A. So right now, in this case, we have piece number 1 here, piece number 2 here. If we make it or take them individually, so this is the first segment, which is 1 here, and this is the second segment, which is 2 here. So the shear, let's let's start with the normal force. The normal force here is going to be positive إذا كانت إيش tension أو tensile force. Shear حكينا it's going to be positive if it's going to rotate the piece of the structural member clockwise. يعني الشير لازم يكون positive إذا shear force راح تعمل rotation for the structural member piece clockwise. يعني إذا تخلي هاي القطعة تلف باتجاه عقارب الساعة. Bending moment is going to be positive if it's going to bend this piece and make it concave up, يعني bending upward. هذا البندing. In the other case here, normal force positive and they are equal to each other. Shear it's going to be this way عشان تعمل rotation له زي هيك. والmoment كمان لازم يكون ايش؟ This way, okay? These will cancel each other if they get back together. This will cancel each other and these will cancel each other. Hey, the sign convention. Let's take an example and see how we can find the internal loadings, which is normal shear and bending moment diagrams for a beam. Okay, in this example, the problem statement says determine the normal force and shear force and bending moment acting just to the left of point B and just to the right of point C of the 6 kilonewton force of the beam. هون شايف بس this is an example to show you إنه it's a matter إنه أكيد الشير هون بيختلف عن الشير هون، okay؟ وبيختلف عن الشير هون مثلا. And it's not the case here, but sometimes it might be a different if we do have a force somewhere. يعني كل ما يتغير عندنا الفورس أو الكروس سكشن راح يكون عندنا إيش؟ different shear and bending moment diagram. Okay. So first we need to take or to find the normal shear and bending moment here قبل القوة هاي. Okay. يعني this force is not gonna be considered. So here, for this beam, we do have a rocker here, which is one force component, and call it AY, as you do see here. This is the free body diagram, let's say. So we do have AY here. We do have two force components here. This is, let's call it DX, and call this dy, okay, which is here. This is dx positive to the right, this is dy positive upward. So we need to find these support reactions before we proceed to find the internal force at point B and C. Okay. So here if we take the moment at point D, and again at point D because we want to eliminate more unknowns. And hon, if we do take the moment here, dx and dy, they will be out, okay? So summation of moment D is equal 0, positive counterclockwise. This is our assumption. So what we do have at D we do have a moment here. And this moment is counterclockwise, so it's going to be ايش؟ positive 9 kilonewton meter. هذا المومنت أول شيء هون. طبعا moment it's a free vector, okay? It's not going to be multiplied by something. And we do have the force here. The force is going to be 6 kilonewton times the distance between D and the force point of application, which is 6 meter. طبعا positive because it's going to rotate the beam counterclockwise, and AY here minus AY times the distance, which is 9 meter. So AY here is 5 kilo in Newton. So once we got AY is equal 5 kilo Newton, we can get dx and we can get dx and dy here, okay? But in this case, we don't need to find it. Our section is going to be one time here and the other time is going to be here. يعني قبل وبعد هاي الفورس, okay? So let's take the first imaginary cross section. So we made a cross section at point B, and point B is before the 6 kilonewton load. يعني قبل القوة اللي هي 6 kilonewton. It's not going to be in here. طبعا AY we got it 5 kilonewton. Right now, this is normal force, positive as a tension here. This is shear force, positive if it's going to rotate the piece here clockwise. وهون bending moment positive, if it's gonna pin the structural member piece and make it concave up. And هون once again, sign convention is arbitrary selection. يعني أنت بتقدر تختار اللي بدك إياه. ممكن تختار النورمال this way، تختار this way، المومنت الشير بدك إياه. بس بالأخير the final answers will tell you if your assumption is okay or is the opposite. ماشي؟ فهون احنا let's go with one sign convention. That's what I just showed you, okay? So in this case, let's just take the summation of f of x equals 0. يعني بدنا نطبق summation of f of x, summation of f of y, and moment at a point equals 0. So here summation of f of x equals 0, assuming it's positive to the right. Okay? So we do have MB, normal force at B, and we do have nothing else in the horizontal or in x direction. So MB is equal 0. طبعا, let's see the shear here right now. So, and if we take the summation of f of y equals 0, assuming it's positive upward here, شباب, we do have 5 kilonewton positive upward minus VB, which is the shear at point B, minus لأنه downward. ماشي, احنا the sign convention this is going to be positive, بس هو هون بنطبقه ايش؟ negative, لأنه احنا عاملين assumption إنه ايش؟ positive upward. So negative VB and equals 0. We do have nothing else. So VB here is 5 kilonewton. Okay. So we got normal force, we got the shear. What about the moment? The moment here, if we take the moment at point B equals 0, or summation of moment at point B equals 0, assume it's positive counterclockwise, as you see here, guys. Okay. So here we do have moment B positive لأنه إحنا فارضينه إيش in this way, فهذا it's going to be positive counterclockwise, minus this force here is going to rotate the beam clockwise, so it's going to be minus 5, which is the magnitude of the force, times the 3 is the distance. So minus 5 times the 3, and this equals 0. So the moment at point B is equal 15 kilonewton meter. طبعا هون at this point B. For sure it's going to be different from the normal force shear and bending moment diagram at point C. يعني point C راح يطلع لنا إجابات مختلفة. طبعا ليش؟ لأنه إحنا هون we do have a force. Okay. Point C اللي هي after the اللي هو 6 kilonewton force. طبعا it's after, يعني it's just right or left, يعني مباشرة, فيعني 6 kilonewton is going to be in that point. طبعا هاي بس مثال توضيحي. Later we don't want to go with such examples, راح تكون الأمور أكثر أوضح. Okay. So in this case, guys, we do have this piece here. Okay. This is A, this is point C. Same, because the distance here is 3 meter, because I just told you it's just right or left to the force here. So in this case, summation of f of x equals 0, assuming it was to the right, and see here, normal force is equal 0, this one. طبعا هون same sign convention, okay? Summation of Fy equals 0, assume it's positive upward, so we do have 5 kilonewton minus, don't forget this, minus 6 kilonewton, okay, minus Vc equals 0, so Vc is minus 1 kilonewton. طبعا minus Vc يعني انه ال Vc بدها تكون بهذا الاتجاه عندنا. اوكي. يعني هون بنقدر نحكي or let's come on here. Vc is 1 kilonewton upward. Okay, that's okay. Okay, what about moment C here? Moment C, summation of moment at point C equals 0, assuming it's positive counterclockwise. So we do have minus 5 times 3, which is the force times 3, and it's clockwise, plus MC. طبعا 6 kilonewton is not going to be, or is not going to contribute to this moment, لأنها it's at the point C. خلينا نحكي هون. Moment C is equal 15 kilonewton meter. Okay, so this one, and the direction as indicated in the Hibbeler diagram, counterclockwise. So this is the way how we get the normal shear and moment diagram at imaginary cross section. لما أحكي imaginary cross section فعليا we don't need, or we don't do the sectioning here. بس احنا just to simplify the thing and to find the internal forces for or at any point. Okay, let's take another example here. In this example, we do have a cantilever beam here, loaded with a triangle distributed load, which is this one here, okay? And we need to find the normal force, shear, and bending moment diagram at point C. This is the point C, okay, of the beam, which is this beam. So here, in this case, we have two ways to do it. And one of them is smart and one is not. Let's see how's that going. So in this case, if we take this part, okay, that means we need to find the support reactions here. Okay, بدنا نوجد هاي أول شيء support reactions بعد هيك نحل. The other thing, to take this piece, which is this one. So in this case, we don't need to find, there is no supports here to find the reaction. So in this case, let's go this way. Take this cross section, which is this piece اللي هي شباب ايش؟ CB. طبعا you're gonna take it with its distributed loading with dimension إلها كم 1.5 meter. Okay, so this point is unknown for us. Okay, this point was here, okay, 1200 Newton per meter, but this one is unknown. So if we use the symmetry property for triangles, okay, let's use the similar triangle. So we do have this one here, the small triangle, and this is the point that we are looking for. And we do have the bigger one, or the bigger triangle, which is this one. Okay, so this point we know it. With this distance we know it. With this distance it's given to us. So right now, just like تشابه مثلثات شب اللي هو 1200 dividing by 3 is equal y اللي هو this point which I'm looking for, this height, dividing by the distance اللي هي ايش 1.5. Okay, so y here is equal 600 Newton per meter. And so we got this value. So right now, instead of this, just a minute, put this much اللي هو 600 Newton per meter. And this is exactly at this point. This point is different, this point is different, and so on. So here we need to find the normal force, shear, it's going to be this way. So this is BC, this is NC, and the moment is going to be this way, which is MC. Okay, so here guys, just let me take this away. So here we do have a structural member loaded with a triangle of distributed load. So how to find the shear here, or the normal force, let's say. For the normal force, the summation of f of x equals 0, summation, positive to the right. So we do have minus NC, okay, equals 0. So NC is equal 0, okay. If we take the summation of Fy equals 0, assuming it positive upward, we do have VC, okay. What else? We have the resultant force of this distributed load, which is going to be here. The resultant force of this is going to be the area under the loading diagram, which is, this is a triangle. So this is going to be 1/2 times the height, which is 600, times the base, which is 1.5. يعني نصف القاعدة خلينا نقول 1.5 بالارتفاع اللي هو 600. This is the area of this triangle, means the force or resultant force. Okay, so this one is equal to 450 Newton طبعا. It's in Newton right now, okay? And it's located where? It's located at 1/3 from this side. 1/3 of which is 1/3 of L طبعا 1.5 dividing by 3, so this is equal 0.5, which is this distance here, and the rest here is 1, which is 2/3 of L, 2/3 of 1.5 اللي هو 1 أو اللي هي 1.5 minus 5 هاي راح تكون 1 meter، راح تكون 0.5 meter. Okay, right now apply or continue with this summation of Fy is equal 0. So Vc is upward, so it's positive, minus the resultant force, which is this much, okay, 450, and we do have nothing else, so this one equals 0. One equation with one unknown, so Vc is equal 450 in Newton, and the direction as indicated in the figure diagram, upward. So right now we got the normal force, we got the shear force. What else? We need to find the moment here. So the moment for this one, moment C, if we take, let's make it here, if we take summation of moment MC is equal 0, assuming it's positive counter clockwise. We do have, this is MC. MC is going to be ish minus MC because it's clockwise on, okay? So it's minus MC. Okay, what else? We do have the resultant force here, which is command minus 450, this is the force magnitude, times the distance, which is between the resultant force location and point C, اللي هي 0.5, and we do have nothing else. So this one equal 0. So solve this equation. MC will be minus 225 in Newton meter. لما هون minus طبعا احنا we did assume it clockwise, okay, here in this one here clockwise, so means MC is counterclockwise. You either go with this one but keep it all the time minus, or انك تعمل 225 Newton meter وتعمله ايش counterclockwise. So by this we got the shear, normal force and bending moment at point C, and you can do it here or here or wherever you wanna do, okay? So it's gonna be different, but in this case, because it's loaded with the same triangle distributed dot, we will not have that difference, okay? One more example here, guys. In this example, we need to determine the normal force, shear force, and bending moment acting at point B, and this is the point B of the two-member frame shown. This is just a frame because it has more than one structural member. So we care about this beam. In this beam, we do have a pin here. We have a link here at point C. So this link has a force, let's say, either towards the point C or away. It's okay to assume it whatever you want. ممكن تعملها assumption in this way, okay? So in this case, this is the beam, okay? Right now, this is the Hibbeler diagram for the beam. Okay, here it is, this one. So we do have AX, AY at A, we do have FDC at C. So right now, if we take a section at point B, which is going to be here, So we might go with the right side segment or left side segment. And all the time you should get the one with less calcs, with less calculations. So in this case, we need to find the force here if we decide to go with this one, or to find the moment or the reactions at point A if we're gonna decide to go with the left side segment. So I would prefer to go with right side segment. So in this case, but we need to find this force. So if we take the moment here at point A and make summation of moment at point A is equal 0, assuming it's positive counterclockwise. Remember guys here, this is loaded with 50 pound per foot, okay? هذا 50 pound per foot. And the resultant force is equal 50 times 8. Okay, this is the whole distance, 8 feet, and this is 400 pound located at the midpoint. So this is going to be 4 as you see here, okay, 4 feet. So in this case, minus 400 pound times 4 feet, minus because this tends to rotate the beam clockwise, plus the vertical component of this force is 3/5 times F dc. How is that? Imagine this as a triangle like this, Shiba. So this is a 3, this is 4, and this is 5, and this is theta, okay? For the force here, which is the vertical component, okay, which is this one, guys, it's gonna be the force times the cosine, and cosine this angle 3/5, okay? So that would make it 3/5 F dc. For this one, it's gonna be just like 4/5 F dc, okay? But in this case, this will not contribute to the moment at point B, or sorry, A, because this is the line of action of this force passing point A. There's no perpendicular distance there, simply. So this is gonna be this force, the vertical, which is this much, times 8 feet, which is this distance, okay? And we can find FDC. Right now we are ready to go. So this is FDC here, okay? And it's loaded with 50 pound bare foot, which is this much, okay? And here we do have normal force in this way. We call it MB. We have shear this way, we call it VB. We have moment at B. طبعا يا شباب احنا هون ملتزمين بالساين كونفنشن اللي اعتمدناه بالبداية. So in this case, get the resultant force for this, which is 50 times 4, واللي هي 200 pound, located at the midpoint اللي هو 2 feet. ماشي؟ بس نعمل resultant أو equivalent resultant force distribution أو distributed load. In this case, if we take summation of f of x equals 0, summation of f of x equal 0, assuming it's positive to the right, we do have minus n b, okay, minus. Okay, what else? We do have the horizontal component of this force, which is a plus this force اللي هي 333.3 times 4/5. أوجدناها هون يا شباب، okay? 4/5. This equals 0. From this, we will get an B. So MB is equal 267 pound, okay? This is the horizontal component of this force, which is FCD, okay, or DC. Right now, similarly, if we take the summation of f of y equal 0, we do have minus 200 pound, it's minus, which is this one, 200 pound, طبعا minus VB, It seems there's a mistake in this textbook. Okay, let me do it again here. Summation of f of y equals 0, assuming it's positive, upward. Okay, we do have minus 200 pounds. Okay, plus VB, because we did assume VB upward here, guys. Okay, for that there is a mistake here. This should be plus. Okay, plus VB plus the vertical component of this one, which is the plus هون 3/5 FDC اللي هي 333.3, and this one is equal 0. So if we do calculate this one, VB is equal 0 طبعا, equal 0 because this much is almost 200. Okay, طبعا هي بس هون المشكلة, this result is okay. Right now we still need to find the moment at point B. So the moment, if we take the summation of the moment at B equals 0, assuming it's positive, counterclockwise, so we do have minus MB okay, minus MB, and this is clockwise, minus 200, which is this one, guys, times 2 feet, which is this distance. So minus is gonna, because it's gonna or tends to rotate the piece clockwise, plus the vertical component of this is gonna be اللي هو طبعا 200, 3/5 times FDC, which is 333, times the distance between the point and C and B. So the distance here is 4 feet. So right now this equal 0. Okay, one equation with one unknown. So MB is equal 400 pound-foot, and the direction is clockwise. So we're done with this example, and thank you guys for your listening. If you have any question, please chat with me on Microsoft Teams or email me at my school email. And inshallah, next time we're gonna continue and find the shear and moment equations and how to draw the diagrams for shear and bending moment. ويعطيكم العافية.